So as we discussed, right? So the notion of completeness for space classes or for any class, it all depends on what you put over there, right? So right here we have defined p-space completeness with respect to polynomial time. So these are the same kind of reductions one does for NP completeness. Does that make sense?
Yeah.
So on the other hand, when we are looking, this isn't the only notion of a reduction, right? You can define reductions essentially through any time or space constraint.
Mm-hmm.
And one can also, so the idea is like when one looks at NL or one looks at classes inside P, then your notion of a reduction cannot be polynomial time. Otherwise, you get trivialities as we discussed. So we need a more efficient notion of reduction, which is the log space reduction. So we will talk about log space reduction. That is, reductions that can be computed in log space. And this is going to require some definition, but once we get that, then we have another notion of reduction, which is log space reductions, which you can think of as a more stringent version of a reduction than a polynomial time reduction. You could think of doing log space reductions for p space or for NP or anything, but typically what happens is outside of P, one talks of efficient reductions using polynomial time, and that is what is used to define completeness. Within P, one uses log space reductions. But as we will actually see that log space, all the reductions that we've actually come up with are, at least the NP completeness ones, are actually log space reductions.
I see. Is there any notion of like polyspace reductions that you use?
You could do a polynomial space reduction if you're going to look at things within, let's say, exponential time or maybe non-deterministic exponential time. Then you might end up using like polynomial space reductions. I have not seen that specifically, but then again, my knowledge of complexity theory beyond that is less. There are interesting problems in exponential time and exponential space, but if I'm not mistaken, the completeness there is again done with respect to polynomial time reductions.
Okay. I had two more questions from last lecture, but I guess should I wait?
No, go ahead. I mean, I think this is good to clear this up before I get into today's lecture.
Sure. It's kind of a little different, but a little tangent. But I was wondering if QBF is in NP and if SAT is p-space complete.
Sorry, say that again.
I was wondering if QBF is in NP, and another question was that is SAT p-space complete.
So actually, okay. So let's look at what would happen if that did happen. So we know that QBF is p-space complete.
Right.
If QBF was in NP, then p-space would be equal to NP.
Oh, okay.
Because you could take any language in p-space, convert it to a QBF instance, which can then be solved by an NP machine.
Okay, gotcha.
Right, so it's actually unlikely that we think QBF would be in NP. Indeed, specifically, if QBF was in NP, then NP is equal to co-NP. I mean, that's the simplest thing, but much more would happen. But just as an example. And it's worth discussing that this point. So let me bring out what QBF is, right? So, sorry, my notes are all over. Remember, so QBF has more general quantifiers. So if you had lots of alternating quantifiers, it seems unlikely that you would be able to give a certificate for this being true, because it seems like as we discussed in p space versus NP, it seems like you have to look at the entire, this sort of recursion tree. Right? So do you recall this notion of like, Sudoku, the NP version and the P-space version where you're playing against an adversary? So in NP, you just need to find some path down that will take you to an answer, which is a solution, which is a satisfying assignment. Whereas in P-space, like in QBF, you have to kind of look, it seems like you have to look at all the paths. So that's the best way we know how to do it. So it seems that NP is not going to be P-space. I mean, again, like this is all conjecture.
Gotcha. Okay, that makes sense.
And there was a second question that you had after that.
It's basically answered by what you said. I was asking if SAT is P-space complete, and that again would imply.
That would again imply exactly the same thing. It would imply that then QBF can be reduced to SAT. Right? Either of these things would imply that QBF can be reduced to SAT. Any other questions before we proceed? Okay. If not, then let me proceed with. So what I wanted to talk. Sorry, go ahead. Yes.
I guess logistical question. When's the midterm for the class?
When is the midterm? I'm probably not going to hold a midterm.
Okay.
Yeah. I don't know. Like, it depends on. So the main topic for today is to discuss NL-completeness. So remember, we have L is log space, NL is non-deterministic log space. And what I want to talk about today is, just as for every class that we've discussed, we have this canonical problem that seems to capture, that's like the hardest problem in the class, that sort of captures that entire complexity class. Like we have SAT, we have QBF, and I'm going to talk about something for NL. So that NL, you might think a non-deterministic log space Turing machine. Like what is that? And we'll see. We'll actually give you a concrete example that'll make it real. Okay, so L is going to be in NL is in P. Now, as we said, the naive definition of NL completeness would be as follows: L is in NL, and for all L prime in NL, L prime reduces to L in polynomial time efficiently. Now, the problem with this definition is because NL is itself contained in P. What this would mean is, in polynomial time, you could just decide L prime. And so you end up with trivial reductions. Essentially, what it would say is that any non-trivial language in P, or in NL, any non-trivial language in NL is NL complete. Right, which is not sort of the answer that we're looking for. Every non-trivial language, and as I discussed, if you take any language, L prime in NL, since NL is contained in P, given any x, you can basically think of a machine that just decided whether it's in L prime in polynomial time. And if it's in L prime, then it's just going to output some W in L. And if it's not in L prime, it outputs some W prime that's not in L. And we assume that W and W prime exist because L is a non-trivial language. It's neither empty nor all strings. For all, let's just say for all lengths. So let's not worry about that. So essentially, as long as and this needs to be of polynomial sized in NX. So as I discussed earlier in answering the questions, we need a more efficient notion of reduction. That is something that can give us a lens within P. And that notion comes from a log space reduction. So first, let me explain what a log space reduction is. So we have a function which is said implicitly log space computable. Now the problem with log space is that you might think that if you have some input of size n and the function is computing a reduction, the output may also be of size n. How could you actually represent the output in log space? That's not possible. So what we essentially say is that a log space computable function is one where any bit of the output can be computed in log space. Okay, and so we can go through, there's a formal definition of what that is, but this is this is sort of the essence of the definition. So what this means is, here's my input. This is x. What I want to compute is f of x. So a polynomial time reduction would simply take x and compute f of x, would write it out in its tape. An implicitly log space computable function just says that if we give it some index I, then this bit can be computed in log space. So we specify, so think of the input now becomes x and I, and we have to compute the ith bit of f of x. And so we're assuming that, I is going to have size essentially at most logarithmic in x, because I is an index, and we think of f of x being polynomial sized. Okay, so since f of x is polynomial size, I is going to be of logarithmic size, to just specify the index. So does this make sense? Any questions about what it means to be log space computable? Okay. Now, given any two languages, I'll use B, C for languages here because L is something that we're using for log space. So I'll say languages B and C. B is, log space reducible to C, which is if the reduction f is implicitly log space computable. So there is a function that takes, instances. So we have this function. Remember, the picture of the reduction is you have yes and no, yes and no. This is for B, this is for C, and the reduction has to map yes to yes and no to no. And this function f is implicitly log space computable. Is implicitly log space computable. Like, this is what it means. Any questions?
I guess for the wording part, is implicitly there because we're going bit by, like we can consider it bit by bit?
Yeah, exactly. It's bit by bit. So if you were to, formally speaking, if you said f is log space computable, then there might be this confusion that you're actually going to output f. And so you're not going to output f, but rather output a single bit of f. And that's why it's the term implicitly log space computable is used. So now with this sort of definition, or with this notion, we can now define what it means to be log space complete. So I'll say a language C is, I'm sorry, not log space complete, but NL complete. Is NL complete if, and now we just follow our basic template. C is in NL, and we say for all languages B in NL, B has a log space reduction to C. So NL complete languages are like the hardest languages in NL. And just to give you the sort of picture here, so note that we can also define P completeness using log space reductions. Right? This would mean that a language that is P complete is one that you can reduce any language in P to this language using log space reductions. So log space is like that gives you the lens to now view what is going on within P. So here is L, which is in some sense like the smallest language we look at. And then you have NL. And what you here have here is NL-complete. And then over here, you would have P-complete. And of course, just like you have NL, you might define something called co-NL. And of course, there is the surprise that NL is going to be equal to co-NL, which is a surprise. But ignoring the co-NL and NL, this is sort of the picture. So you're getting this picture just like we had this picture within, sort of in P space. You had P, you had NP, co-NP sitting in P space. It's almost like that, where you have L, NL, co-NL sitting in P. Okay, so sort of we've switched time and space. Now, the smallest class we're looking at is a space class. Previously, the smallest class we were looking at was a time class, P. But now we're replacing that with L, being the sort of the smallest unit that we're going to look at. Any questions about this? So I'm not going to be delving into P-completeness in this lecture, and this is something that we will probably come back to when we talk about circuit complexity. Okay, so this is what it means for a language to be NL complete. Now, if you remember that reductions had this sort of chaining property, right? So we would say something like if L has an efficient reduction to L prime and L prime has an efficient reduction to L double prime, then L has an efficient reduction to L double prime, and this is this uses the closure of polynomials. And this is critical for any notion of completeness. Right? Because the way that you prove NP completeness is, instead of going back to Cook-Levin, you would say, okay, let me now start from a language that is already NP complete. And let me reduce that to my new language. Right? And then I get this new language is NP complete. So you need something similar for NL as well, where you would say, okay, so here's my language C. You would like to argue this, but now this is not as trivial anymore, because there isn't a Logspace machine that actually produces the entire output. There's only a Logspace machine that produces any bit of the output. So you have to be a little careful, although the proof is not hard. But I'd like to walk through this just so that we understand this notion of NL completeness better. So let me just state that as a theorem, and let's prove it. So we'll say let F reduce C to C prime and G reduce C prime to C double prime. And so F is implicitly Logspace computable by a machine, by a Logspace machine MF, and G is implicitly Logspace computable by a Logspace machine M sub G. And what we would like to do is we want to construct a reduction H that is also, I'll say implicitly Logspace computable. We want to construct a reduction H from C to C double prime that is implicitly Logspace computable. Okay, so is that clear? So let me sort of sketch out the basic construction. And then, if you want, I can then go in and fill in details. The key is to get the idea. The idea, once you get the idea, you'll see that it's not very complicated. I want to make sure that everyone is on the same page. Do you understand why? I mean, of course, every statement needs a proof, but do you understand why this is not obvious? In this reduction, you would just have you could just chain these two polynomial time machines together, right? You would run the first polynomial time machine. You would get the output. And then you would run the next polynomial time machine on that output. With this, you just have to be a little careful because it is implicitly Logspace computable. So what you need is to be able to sort of chain these Logspace machines together. The problem is, okay, so let me give you the failed proof and tell you why that doesn't work. So here's like, a failed proof. So you could say use, okay, so let's start with x. M of f can write down f of x in log space by, okay, so essentially remember M of f will take as input x and I, and we'll write down the ith bit of f of x, can write down f of x in log space by taking input xi for all I, and I is going to be at most some polynomial. So for all I, that's at most some x to the c. And so M of f has written down f of x. Then f of g can write down f of g. Now if you want it now, and so what you wanted to do was you wanted to compute the ith bit. Okay, so we can write down the ith bit of g of f of x using, so this is not the same I, so maybe I'll just say the jth bit using m of g. Alright, I should say using Logspace. So this was a Logspace machine, and this is a Logspace machine, so totally it's Logspace. So where's the hole in the proof? What's wrong? Okay, so first, show of hands. Do you understand the failed proof? Like, do you understand what I'm trying to say here? Do you understand? Do you see why this gives the reduction? A for yes and B for no. Because I think maybe it's worth, let me just repeat the idea over here, because then I want you to tell me what the error is, why this proof doesn't work. I'm just trying to recreate the proof that polynomial reductions can be chained together. So let's say I have a reduction from L to L prime and from L prime to L double prime. So I know that there is an algorithm that takes an instance and converts yes instances in L to yes instances in L prime and vice versa. And so I just run that reduction. It's a polynomial time machine. It's going to take some instance, it's going to produce some output. Then I take the next polynomial time machine, run it on that output to get the final output. I'm just going to do this. I'm just going to use the same logic here. I need to show that H is implicitly log space computable. So what is H? So H of X should be G of F of X, right? It's just composition of functions. So I want a machine that works in log space and computes the jth bit of this in log space. So let's just start with X first. Now we know that for any I, we can write down the ith bit of f of x in log space. So I'm just going to go ahead and write down all of f of x just by incrementing I. I just start with 0, 1, 2, 3. Write down all the bits of f of x. Then I take my next log space machine, m of g, and that is going to write down the jth bit of g of f of x because f of x is now its input. And that gives me the reduction. What's the catch?
J might require other bits of f.
J might require...
So G might require other bits of f to get J.
Right, but I've written down this for all I.
Oh.
So we know that between that h of x and then g of f of x, for each bit, between the first and the final product, there has to be a log. There has to be, it has to compute I for in a log space amount of time. So I guess maybe the problem could be that between if you're taking the ith bit between both of them after the first reduction and the second reduction, it's not guaranteed that after those two reductions it'll be in log space for each bit.
Well, I mean, okay, so you guys seem to be sort of kind of getting towards something but not catching the main point. So
yeah,
is the main point that writing it all down might be too expensive?
Writing what all down?
Writing all the bits of f of x.
Exactly. You have to write down f of x for this argument.
Oh, I see.
But that requires this. That requires these many bits. That's polynomial. Remember, instances, you take x, f of x might be large. Remember, in implicitly log space computable, the size of f of x is polynomial. F of x has polynomial size, but each bit can be computed in log space. You cannot afford to write the whole output down. You cannot afford to write the whole output down. Maybe let me draw a picture here.
To clarify one thing, the reason we allowed that in the first place is because the input tape is not counted in our space.
The input tape is not counted in exactly. But the problem is, the way that you chain these is you have an intermediate tape which takes the output of one and pipes it to the input of the other. That intermediate space is actually now workspace. It's not input space. Let me say this again. So here's x. Here's m of f. Alright, so m of f is going to read this. It has its workspace. So this is its workspace. And it can go ahead and it can write down. So given x and I, it will write down the ith bit of f of x. And that's what it's going to finally output. So what we said is, well, okay, you can keep changing this, But then you would eventually have to write down everything. And then you would write down all of f of x. And then you use m of g here. M of g is now going to read this. Once all of this has been written down, it has its own workspace. And then it sort of would output the single bit over here, which is g of f of x of j. And over here we could then like append a j over here. But you see that this is also workspace. This is also workspace because the only input in the end is here. That's the input. And that's the output. This is the input. That is the output. The intermediate space is blowing up when you try to chain these together. Okay, is this problem clear? Is the problem clear now?
I think I understand it now.
Okay, so hopefully this picture sort of helps you see why chaining it isn't that obvious anymore. So how are we going to resolve this problem? Any ideas? And I'll give you a hint. Instead of running mf first and then mg, think of the opposite.
Why not just immediately run mg on once you receive a bit from mf, and then just repeat and then reuse space?
Well, mg might require many bits. mg in the end is going to probably read through the entire input.
Right. But can't you just say, like, if you know, because all you have to do is determine this property for every bit, right? So you don't even need to write to store every single bit, right? Like you don't need to write down every bit of either input, right?
Right. You don't need to write down every bit of f of x.
Right.
But why? Right, that's the key. Okay, so why is it that you don't have to write every bit of f of x?
Because there's no reason to. I mean, you just need to, for each bit, you just need to run mg, and then if the output of that is also in Logspace, then you can just erase everything you have and just move on to the next bit, right?
Wait, so you have to be careful. So let's go back and look at what the input is. So we want the jth bit of g of f of x. So what is the input going to be? The input is going to be x and then j. Okay, so now what? And so here's mg. But mg is supposed to take as input f of x. Not just one bit of f of x. It might need all of f of x because it might scan through the whole thing to figure out various things to compute.
That's right.
Right? So one bit of f of x is not enough. But this is going on the right track.
What about something where you kind of compute g for different variables, or like different types of bits? Like you have like if statements, like if it's this and this and this, and then you just kind of fill that out, and that way you're saving the space.
Yeah, but I mean, you don't know what these machines are actually doing, right? At this point, these are black boxes. So you don't want to go into the machine and look at what it's doing because that seems like you have, all bets are off, right? You have no idea what this machine might want to read. think of it this way. Let's look at the running of MG. Let's look at this picture. So at any time when MG runs, what does MG need? For one operation of MG, what does it need? And it's got these heads, right? So the workspace is small. What does it need from here just to run it at one step?
Well, I guess it would definitely need the first log characters of the input, right?
I mean, but even more simpler, what is the head reading?
Well, the first character.
Or some character.
Some character.
So the head is reading some character. So all it needs is this character, after which MG can transition its state, output the update the workspace, and move the head left or right. Is that correct?
Yeah.
So when it needs to read this bit, it doesn't need to store all the other bits. All it needs is that character, which we're thinking of as a bit. So when it needs that bit, this is some k. It needs the kth bit. It goes and runs this machine for k, gets that bit, and then if it transitions left or right, it says, okay, now I need to read the k minus 1 bit or the k plus 1 bit, which it now stores in the workspace. So the workspace stores an index of what needs to be read. Right, this is works badly written. So MG simply stores where the head is. And when it needs the bit from there, it runs MF just to get that bit. And then it updates the head position. The position of the head can be stored in Logspace. Okay, does the simulation make sense? I'll walk through it again and I'll write some stuff down. But I think, if I write it down without you seeing the picture, it's not going to help. Think about this machine, except you don't want to write all of this down. But let's just, as a thought experiment, say, suppose this actually wrote everything down. Just like imagine. And then you need to run MG. What is MG going to do? MG let's say at any point, the workspace is going to store the index of where the head is, where this head is. So this is the head index. And so MG stores the head index. To get the character there, MG runs MF with X on the head index, gets the character, makes the transition, in which case the head is going to move left or right. So the head is now going to go to k minus 1 or k plus 1. So it updates the head index, and then it proceeds in this manner. So does this make sense?
I see. So there's no reason to store anything besides the head position and just some workspace then.
Exactly. All it needs to store is the head position. And the head position can be fit in Logspace.
I see.
It requires a double take. We have to think about it, right? So because what you recognize is that the Turing machine, and this is the benefit of looking at things in terms of Turing machines, as opposed to looking at algorithms, the Turing machine is just reading a single bit at each step. Like each operation of the Turing machine, it reads a single bit. So as long as that bit can be computed in Logspace, that's good enough. What is needed to compute that bit is the index of the head. The input just has X, so that will always be there. This additional index, that can be given in Logspace. So another way to think of this picture is here is mg. Now mg has to output this. I mean, technically one can embed this in the state, but I want to just write it out as an output. It has a workspace, so it's going to be, the workspace is going to be divided into three parts. This is the workspace of mg. This is going to be the index of the head. This is not the real head. So this is the index of head, or you can think of the index of f of x that the head reads. And I put head in quotes because this head is actually not even going to be reading that. And then it's going to, the third workspace is going to be the workspace of mf. This is the workspace that it's going to have. And its input is of course just x. So here is how this, and so now this is not the machine mg, but rather I'll say this is the machine mh, because this is now going to compute g of f of x. It's going to compute everything together. How does this work? So let me tell you how a specific transition works. So at any stage, so I'll refer to this as k. K has some value, and mh is simulating mg. So how does a simulation go now? mh runs mf on x and k. So x is part of the input. It knows what k is. It runs it to get f x k. Now based on f x k and the state of mg, because it's actually simulating mg, based on the state of mg and the workspace of mg. So it's also reading the workspace of mg. Determine the next state of mg, and whether head of mg's input moves left or right. So remember, mg, we're not really writing down the input of mg. We're sort of implicitly computing it as and when needed. And then, if it's a left, decrement k, else increment. Okay, and then you go back here. So this is going to simulate mg. This is a simulation. This is a Logspace simulation of mg on f of x, on the input f of x. But we're never really writing down the input f of x. And the important thing is k can be stored in Logspace. Okay, so that completes the simulation And so just to be clear, the workspace of M of M of f, that's going to be at most log of x, which is, that's log space. Sorry, just a second. So that's at most log of x. What is the workspace of M of g? This is going to be log of f of x, which is O of log of x, because f of x is at most polynomial sized. So it's just O of log x. And the index of the head, this is also log of f of x, which is O of log x. Sorry, this is a bit of a mess, but you see that all of this is just log space. So this is a log space simulation of M of g on f of x. And so that basically ends the proof. One has to, if one were to write the details, one would basically sort of write this out. Let's pause here. I'll take your questions before coming to sort of the next part of the lecture. Okay, good. So now we have this theorem. And the theorem is that log space reductions can be chained. Like, that's the punchline, right? So now you actually have a theory of NL-completeness. Just like you have a theory of NP-completeness, you can look within P and you can try to understand what NL-completeness is. And as soon as we did NP-completeness, we introduced this language SAT, and we said, no, SAT captures NP-completeness. SAT is NP-complete, and it's like a canonical problem. And now what I'm going to tell you is that for NL, there is a very natural problem that happens to be NL complete. And that language is called, well, it's called path or directed path. And directed path is the following language: G, ST. G is a directed graph. ST are vertices, and there exists a path from S to T. So I'll just call it D path. Sometimes it is referred to as path. Often you'll just even refer to as just path. So I'll just call it as path. I put the D there initially to specify that this is a directed graph. Does the language make sense? It's just a graph, S and T, and S is connected to, as there's a path from S to T. You can solve this using your favorite BFS or DFS or whatever have you. But remember, BFS and DFS take linear space. Right? So that's a linear space algorithm. But the theorem is that path is NL complete. Sorry, I should have just called this. Path is directed path. When I mean path, it's directed path. Okay, so let's prove the first part. Prove that path is an NL. So let's try to understand what is a log space machine in the context of graph algorithms. So remember, the number of vertices is like the size of the input, like up to that squared. So you can think of G being stored, let's say, as an adjacency matrix. And it doesn't matter. Let's store it as an adjacency matrix just for clarity. Imagine G is the adjacency matrix, and let's say there are n vertices. So how much does it take to store an individual vertex? How much space to store an individual vertex? How many? There are n vertices. How much do you need to store just the label of an individual vertex?
Log.
Log n bits, right? So in log n bits, so in O log n space, we can store a vertex. Meaning, a log space machine can only store O of 1 vertices, or really O of 1 vertex labels. That's what the machine can store, basically. Unless it does something crazy with, with the labels of the vertices, but think of it as all it's storing, it's a bunch of vertices. So let's just think of a log space machine as a machine that stores a bunch of vertices. And it can look up neighbors using the input and counting. So a log space machine, the way to think of it is, what does a log space machine do? It can look up neighbors. So it stores, so what it can store is maybe a bunch of vertices, u1, u2 up to uk. K is just some constant. And now it can go and it can look up a neighbor. It can ask for a neighbor. Right? We can say, what is the ith neighbor of u is uv an edge. It can make these basic queries. So this is the way to think of what a log space algorithm is in terms of the graph. Right? And because all it stores, it just stores a bunch of vertices. So it cannot do BFS because BFS has to store all the vertices that are visited through a crawl, BFS or DFS. So that's linear space. So log space is saying, what can you do with an algorithm that can only store a few vertices? Now path is an NL because the machine can non-deterministically guess the next vertex in a path from S to T. So imagine instead of doing a BFS, it sort of does a DFS, right? But it just guesses what is the next vertex to go to. And the non-determinism will just take it to the end. Does that make sense? The non-determinism will just take it to the end. So path is an NL. So this is kind of interesting, just to step back and say, hey, there is this language which is very natural, for which you have written code, presumably, or you've at least studied this problem, and it's actually even more efficient. There's something that is more efficient than polynomial time, or even linear time. Basically, because it's actually a non-deterministic log space. You don't even need that much memory in a non-deterministic sense. Okay, so is this part clear? So path is in NL. But now we need to prove the more difficult part. We need to prove that for all languages C in NL, the language C can be reduced to path. So we need to show in some sense that the path problem, the directed path reachability problem, is sort of the canonically hard problem in NL. So we have to reduce every language in NL to path. So let M be an NL machine deciding C. Right? So M uses at most C of log n space. C is a constant. So as we discussed, M accepts some input x if and only if in the configuration graph G of mx, C start can reach C accept. So M accepts x if and only if GMX C start C accept is in path. So this is giving us the reduction. We just need to argue that GMX C start C accept can be computed in Logspace. We need to argue that given x, G of mx C start C accept can be implicitly computed in Logspace. Okay? So let me start with the easiest one and then move on to the more difficult one. And so let's actually break them apart. We can say computing C accept in Logspace, C start implicitly in Logspace, and GMX implicitly in Logspace. So we want to compute. So the first part is, let's say, the ith bit of C accept, and this is easy. Doesn't depend on x. Right? This is just a fixed. Remember, we argued the accept state would just be like C accept is simply Q accept blank 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 blank, so on and so forth. So this is something that any individual bit of this is just some function. I mean, it's just something we can explicitly write down. So this is easy. So what about the ith bit of C start? Now remember that C start is going to be, Q0, which is the initial, and then just x. So the ith bit is easy to compute given x. Right? So ith bit of C start is like the I minus theta of one bit of x, where theta of 1 is basically whatever size is required to write Q0. Like this part, you need x, and here it's just something fixed. So the ith bit of C start is also easy to write. Now remember, we said that we can think of GMX as represented by the adjacency matrix. You can think of the adjacency matrix written down just as, just in one row, but it's convenient to just think of being able to index it by two different rows. So the ijth bit of GMX. Okay, so this is important. This is saying, what does this mean? And instead of ij, let me call it the C prime bit. C and C prime are configurations. C and C prime are configurations. And of course, note that the size of C and the size of C prime is O of log n, because that's what you need to store a configuration, because the machine uses log n space. So the configurations all have size log n. This is important, and this is where this log n. So each configuration is of size O of log n. So if you take two configurations that are size O of log n, so you write them down one by one, and a log space, can we determine if C prime follows C according to the Turing machine, the non-deterministic Turing machine transitions of the machine M in log space? And the answer, of course, is yes, because if you're given C and C prime, as we've discussed, like, we just need to check that there is a head and the head moves by one step using the transition function. Basically just have to check that the head moves correctly and all other symbols are unchanged. Right, the head and all other symbols, not touched by head. Right, so we just need to check that if this was the head here, then check that whatever symbol sigma and whatever q over here, the new symbol over there, the new head, follows according to the transition function. And this is something that can be done in Logspace, because all you need to do is look at one symbol here, then go all the way there, look at another symbol over there. So the machine just needs to be able to count, to go from a particular position here to go to the same position in C prime. The machine needs to count. And as long as it can count indices, which a Logspace machine can do, it can basically just go ahead and verify this. So it can determine the ijth bit, or the C prime bit. It can say this is 1 or 0. So it can compute all of these individual bits in log space, and therefore, given any x, it can compute gmx c start c accept implicitly in log space, and this is just a path problem. Now, if you think of configuration graphs, it's almost sort of obvious that you can reduce any instance to the path problem. Right, and the important thing to observe is that it's implicitly log space computable, because essentially computation in some sense is local. So each individual check of, do these two configurations follow? Can one follow from the other? All you have to do is look at a particular bit of the first configuration and look at a particular or symbol of the next configuration, the same symbol, and just match them up and check, so on and so forth. So does this make sense? You may have to go back and sort of look at this proof just to verify all of this, but hopefully the overall idea makes sense. And this is why path is NL complete. Any questions? Any questions about that? I think, let's walk through this a little carefully. So think of a log space machine. And so what does the Logspace machine do? It has the input X over here, and then it has the workspace. And that's pretty much it. And then it has some accept state. So if you fix the input, let's try to represent the entire state of the machine. How do you represent the state of the machine? You store K, because K is telling you which bit of the input is being read. Then you store the workspace with, Q, as we discussed before. This stores the entire sort of configuration. This is a configuration. Does that make sense? So what you need to store is, this is like the entire, not just the internal state, but like the entire state of this machine. You're telling me what's in the workspace, what input bit is it reading, and what is its state, what the state machine state. And you think of this being pointing to that. Now, given X, so think of fixing X and going through all possible workspaces. And just determining, does one workspace follow from the next workspace? Does one configuration follow from the next configuration? Or from the previous, sorry. And that's what this is. These are the configurations. So you give it two configuration strings.
I see.
And you're saying, does one follow from the other? And that you can determine in Logspace, because all you have to do is sort of match up the symbols and just make sure the head is transitioning correctly, right? Which is just some constant time check.
Okay, I think I understand now. So basically, it's like if you have a problem in NL, you can represent like the configuration graph. Well, obviously that's a graph, and then you can find, well, in the path problem, is it you can compute that in that you compute that in NL, and then so you can just see if there's a path between the start state and the end state, and then you can, for each state you can just compare. It's very easy to just compare if one state follows from the next state.
Right. So to be clear, this is not giving an NL algorithm.
Right.
This is giving a reduction from the language to an instance in the path problem.
Right.
The point is, this instance can be constructed in Logspace implicitly. Like each bit of the instance can be computed in Logspace.
I see.
So let's sort of step back, right? Let's step back. So here's L. And we have some X, and the question is X in L? Right? And L is in NL. So what is our reduction going to do? We're going to say, well, there is this M, this Logspace machine, Logspace non-deterministic Turing machine, deciding L. Okay, let's write out all configurations of M. Fixing X, the input is fixed, it's read-only, but let's write out all the possible configurations. Well, guess what? This whole thing is only log n space. Right? Because the workspace is log n, the index it is reading is log n. And so write out all those configurations, they're at most some poly n. So there are poly n vertices in this configuration graph GMX, and the start configuration is some specific configuration, right, where K might be 0 and the workspace is probably empty, is all blank. So C start is something like, this is 0, this is the index K, and then maybe you have the start state Q0, and then you have all blanks. This is what C start is. C accept is, let's just say that when it accepts, it's going to move this back to 0. This is going to be Q accept, and let's just say it makes it all blank. We can sort of force the Turing machine to do this. And so we have this graph now. So here's C start. Here's C accept. And then we have all these transitions. And because it's non-deterministic, it could be making multiple, it has multiple choices for each vertex. So on and so forth. So we know that X is an L if and only if there is a path from C start to C accept. So if and only if GMX C start C accept is in path. So this seems to give the reduction, but there is an important point here. The reduction should be efficiently computed. In our case, efficiently means implicitly log space. So we need to argue that every bit of the input of this, I said input, every bit, so you can think of the reduction f of x is this. Right, this is like the encoding of the graph, the start state and the accept state. So we need to compute every bit of this encoding in log space. And that's basically what I argued here, is that every bit can be computed in log space. And if you go back and you stare at it, you'll see that yes, you can compute every bit in log space because configurations are sort of easy to manipulate or easy to understand in log space. All you need to do is to say, if the head was in the ith position, then go and check the head was either in the I-1th or the I+1st position. And if it went in that position, make sure that that's consistent with one of the transition functions. Make sure that there's only one head in each configuration, and then all the other symbols have to be the same. Like go back like the Cook-Levin sort of idea, and you'll see that all of that is just a log space computation. All of that is a log space computation.
I see. Okay, thank you. I think I understand now.
It's it takes some time to get used to space complexity. It's not very easy or intuitive, especially when when you're used to thinking about time complexity. But just to sort of recap this, okay, so I want to sort of state the main message. What is I said every lecture we do one sort of main theorem. The main theorem here is that path is NL complete. And you can think of, what about the problem U path, which is undirected. This is also referred to as undirected ST-con, undirected ST connectivity, which is just GST. G is an undirected graph. And S is connected to T. And what Reingold showed in, I think it was 2005, is remarkably, he showed that this is an L. There's actually a log space algorithm to do this, which means this is almost unimaginable. There's a graph. You want to see if you can go from one vertex to another. All you can store are a constant number of vertex indices. So you can't even store the path. You can only store a constant number of vertex indices, and you want to be able to check if you can go from S to T. And this uses like a lot of beautiful theory, like from random walks, and it's not a randomized algorithm. It's a deterministic algorithm, but it uses lots of ideas, from constructions of certain graphs with nice properties. It's a very non-trivial result. But this is just to sort of tell you that there are amazing things you can do with log space. So think about a graph algorithm where the only storage you have is some number of vertices. That's it. That's the only storage you can have. And yet, like, it's actually possible to do this in log space. Like, you store 50 vertices, say, as an example, and are actually able to determine if one vertex is connected to another without storing anything. So, like, we sort of saw an example of this even with Savage's theorem, where you can kind of check if there is a path without storing the entire path. But this is even amazing because it's just constant number of indices. I'm not going to be proving this theorem. That would be sort of beyond the scope of this course. But this is to tell you that sort of vertex connectivity sort of captures a lot of space complexity. This isn't and it sort of has lots of connections to space complexity, even as we saw with Savage's theorem. The important point is path is like now this canonical problem in non-deterministic log space. So I'll end here. I'll take any questions that you have, and when we come for the next lecture, we will continue our discussions with NL, and we'll eventually move on to the theorem that NL is equal to co-NL.